Hello, BC Calc students. Today is day 41 notes. For day 41, we're going to be looking at the concept of RAM. And RAM, which I'll explain to you what that means later on in the lesson. We can do LRAM, RRAM, and MRAM. We're going to see all three of those today. And it has something to do with area. So if we look at this example over here, what we're really transitioning over to in the study of our course is talking about finding the area under a curve, which is a huge part of the study of calculus. So it says if f of x is continuous and non-negative on the interval from a to b, we can find the area bounded by y equals f of x, the x-axis, and the lines x equals a and x equals b. So this is a very defined interval of time that we're going to find the area under that curve for. So I'm going to show you some examples, and my question is, do we need calculus for these? So here's an example of area under the curve. Do I need to apply a calculus technique to find the area of this region bound by x equals 1 and x equals 6 and the line y equals 7? No, certainly not. So if we look at this example, we know that that's a rectangular region whose base has a length of 5 and whose height has a length of 7. So if I do just area equals base times height, we would say that in this case 5 times 7 is 35 square units. And I know that you don't have some these diagrams in your notes, so if you need to hit pause at any moment to sketch them quick, of course you can do that. Here are the other two pictures. This one kind of is I'm kind of thinking it looks like the free throw line almost on a basketball court. But if I were to fill in the area of this region right here, do we need calculus to find that area? And I'm convinced we don't, right? I mean, we have a rectangular region plus that little semicircle above it. So based on that, the area would be the rectangle plus the semicircle. So this is a base length of 6 times a height of 6. Plus then we have to take half the area of a circle, so pi r squared, where the radius is 3. So therefore the area equals 36 plus 9 halves pi. And again, this would be square units. Okay. So we've got that one. And then last one, I don't know, do I need calculus for this one? If we have the function y equals 2x is going to be the bounds that we're trying to find the area underneath that curve from 3 to 5. I don't think we need calculus either, guys. Maybe we should just throw calculus out the window, right? Well, if I turn it this way, do you see what this shape is? Isn't it a trapezoid? We can find the area of a trapezoid. So the area of a trapezoid in general is going to be 1/2 the sum of the bases times the height, or sometimes you see it written as height over 2 times b1 plus b2. So let's see, the height actually, if I turn it back this way, the height is the 2 here. And then those base lengths are the y values of where x equals 3 and x equals 5 correspond with on the function y equals 2x. So we said that the height is 2. Base 1 would be 3 times 2, which is 6. Base 2 would be 5 times 2, which is 10. And since 2 over 2 is 1, the area here is 16 square units. So none of these examples required calculus quite yet. But I mean, if it's something that's nonlinear, I mean, what about this example up here? I don't know. Can I break this up into regions that I can find the area of? Probably not quite. There has to be a method or a technique for us to be able to find that area, and we will be able to exactly do that eventually. Today, we're going to talk about methods called LRAM, RRAM, and MRAM that will help us approximate this at least, okay? And since a lot of what we talk about with area relies on summing up some things, why not talk about sigma notation? And you'll see sigma notation kind of pop up in some of the homework examples that are coming up, just to kind of refresh your memory on what sigma means. This is also known as the summation symbol in math. So what we want to do to evaluate the summation from n equals 1 to 4 for 3n minus 1 is we're going to plug in 1 for n, we're going to plug in 2 for n, we'll plug in 3 for n, and then we'll stop when we plug in 4 for n. And whatever those results are, we're going to add them up together. So when I plug in 1 for n, 3 times 1 is 3, minus 1 is 2. And when I plug in 2 for n, we're going to get 6 minus 1, which is 5. And it will make sense to us that these are going to increase by 3 each time according to the kind of slope of that linear term. So again, the summation symbol means take these results and add them up together. So the next term when n equals 3 would be 8. The final term when n equals 4 would be 11. So if we add all those up, it looks like a total of 19 plus 7. So that's 26 here. Okay. So number 2, it already told me which ones to add up. Add up 1 plus 4 plus 9 plus 16 plus 25. What I actually want us to do in this one is express this in sigma notation. Okay. So although we can add those up together and get a total of 55, what would that look like in sigma notation? Well, we're summing up the terms. Let's go from n equals 1. Since there's 5 terms here, we'll go from n equals 1 to 5. And then establishing the pattern that exists among those terms. Hopefully you're seeing it pretty quickly and easily here that this is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So it's for the terms in the sequence n squared. And if we were to do that out, we should get 55 as an answer. In fact, we can probably even double check this on the calculator. What is it, math 0? Is that the trick here? Yeah, math 0 summation. And maybe I'll just do x equals 1 to make my life a little bit easier. To 5, and we'll call that x squared, and I hope it's 55. Did I do it right? There it is, 55. So if you have that option on your calculator, you can do that pretty quickly. So we should be able to do the last one pretty quickly on the calculator, but guess what? We can also do it without the calculator. How on earth is that possible? I mean, do I want you to write out all 200 terms? Boy, this video is going to be a long video if that's the case. No, but there is a distinct pattern here, isn't there? When I plug in 1 for n, we get 3. When I plug in 2 for n, you're going to get out 5. And when I plug in 3 for n, you're going to get 7. And those are going to increase by 2 all the way until the last number I plug in for n, which is 200. 2 times 200 is 400. And then plus the 1 is 401. So how can I do this without a calculator? Well, it's by recognizing and remembering that when these terms increase by 2 each time, it's a pattern in an arithmetic series. An arithmetic series is something you learn in Algebra 2 honors, definitely, again, probably in pre-calc honors. So the formula for an arithmetic series is S sub n equals n over 2 times a1 plus an. So n in this example is, we're summing up 200 terms, 200 over 2. The first term in my series is 3. A sub n is the last term, 401. So that's kind of nice that this is just 100. 100 times 404 is 40,400. Okay, so just a little bit of practice with summation here. And we better double check it on the calc real quick, just to make sure I didn't make any silly math mistakes. Math 0 from x equals 1 to 200 of 2x plus 1 is 40,400. Thought about it for a sec. It was like, I'm adding up all those numbers from 1 to 200 for x. Okay, so there we go. Summation, like I said, will pop up on the homework because the idea of finding the area under a curve y equals f of x can be represented as summation. And here's what RAM stands for. RAM stands for rectangular approximation method. So I know this curve is not sketched in your notes, so I would like you to take some time and try and get a curve similar to mine in your notes. And what we're doing to approximate the area underneath this curve is we're breaking up the interval from A to B into a series of rectangles. And those series of rectangles that I'm breaking the interval up into, they're going to have equal widths across. Okay, so these base lengths going across, those widths, we want them to be equal. So then if I can find the heights of each of these rectangles, then when I take all the rectangles and add up those areas, that's an application of a summation, isn't it? We're summing up the areas of all these rectangles on the interval from A to B. Now, how am I going to find those heights? Well, notice how the height, in the way that I've drawn this diagram, the height is always a y value on the function y equals f of x. And there are different ways that we can draw our rectangles. I'll tell you, this particular case is a case of rectangles that are called inscribed. So inscribed rectangles are ones that are all contained underneath the curve, where one endpoint is on the curve, but the rest of the rectangle is contained underneath. Okay. So what I want to do is I'm going to divide the interval from A to B into equal n subintervals of equal width. And what we're going to call that is we're going to call those delta x. So delta x can be found in general by doing the difference of b minus a, the endpoint minus the start point, divided by the number of subintervals that we'd like. So we're going to define that to be delta x. That's the width of each of these. And again, to find the height, it's really just an application then of finding the function value at, where's the first height? X sub 1, the second height, X sub 2, the third height, X sub 3, all the way until I get down to that last height at X sub n. So the area of all these rectangles would be, in the first case, delta x times f of x sub 1, plus then the same delta x, right? That same width for the next one, times f of x sub 2, delta x f of x sub 3, plus all the way until we get down to the last rectangle that we've, oops, that's an x there, delta x f of x sub n. Okay. So how can we literally sum this up? I mean, it's kind of fun that that's the word that we're using here. We're going to sum this up with a sum. So this is then going to be approximately the summation. We're going to define this as actually being from I equals 1 to n of, in each case, if I sum up all of those rectangle areas, it's always going to be delta x times f of x sub I. So starting at I equals 1, we'll go to x sub 2, x sub 3, until we get to the nth rectangle. We're going to take those areas, add them up, and that will be the approximate area under the curve y equals f of x on the interval from A to B. So definitely starting to get a little notation heavy, and if you love notation, just wait until day 42. And day 42's got a lot of good notation in it as well. Okay, let's take a look at what this looks like from two different perspectives. So if you look at the next example, we're going to look at 1 plus x squared, and we're going to estimate the area under the curve from 0 to 1, first using 4 rectangles. We're going to do this in two different ways. We're going to do this from a right rectangular approximation method. So that's what RRAM stands for. And we'll also do LRAM as well. So here's what I want you to do. First and foremost, we're only looking at this from 0 to 1, so I'm going to try and make this mostly a quadrant 1 graph. And if we think about 1 plus x squared, what that looks like, it's a parabola shifted up 1 unit, right? So I'm going to really exaggerate and extend that off to the side here. And we want to find the area from 0 to 1. Okay. We want to do that using 4 rectangles specifically. So I want to break up this interval into 1, 2, 3, 4 rectangles. And when we say RRAM, the right rectangular approximation method, I want you to start on the right side of your graph, which at this point would be at the end of the interval at x equals 1. And I want you to go up until you hit the curve. And that's the height of your first rectangle. So you're going to come across until you get to the, okay, there's the first rectangle. So then if I kind of work backwards here, coming in from the right, the height of the next rectangle where I hit the curve is right here, come across and down. The third rectangle I'm going to draw in, here's the height, come across and down. And then the final rectangle, across and down, looks like this. So these rectangles, because they are all slightly above the curve, they are known as circumscribed rectangles. And circumscribed and inscribed are words that you learned way back in the day of geometry, the good old days. Okay, circumscribed circles and versus inscribed. Okay. All right. So how am I going to find the areas of those individual rectangles? Well, first of all, let's define what the delta x is, right? We want to find this rectangle, this area, and this area, and we want to add them up. Okay. So delta x is the width of each of these bases here. I mean, it's pretty easy to determine, but if you use the b minus a over n formula, we have 4 rectangles. The difference in those endpoints is 1. So we have kind of a base length for each rectangle of 1/4. And then what we're going to do from there is we want to take that 1/4 and we want to multiply it by the height of each of these rectangles. So this would be what, 1/4, 1/2, 3/4. So if the base is 1/4, the first height would be at f of 1/4. And we'll figure out what that is. And then again, each base is 1/4, but then that's going to get multiplied by f of 1/2 for the next height. 1/4 times f of 3/4. And then finally 1/4 times f of 1 is where that last height is. So you would find each of these areas and then add them up to get your total area under the curve using a right rectangular approximation. Okay, what's kind of nice, I think, about this instance is that you can go to y equals, you can type in 1 plus x squared, and you can make your job pretty easy here. The way I'm going to make my job pretty easy is if I do 1 plus x squared and y1, if I want to figure out what's f of 1/4 and f of 1/2, you can do alpha trace and then do y1 of 1/4 plus y1 of 1/2 plus. So this is going to do the function value that I typed into y1 at 1/4, at 1/2, and so on. So y1 of 3/4, and the last one is y1 of 1. Okay. Now remember that all of these were getting multiplied by 1/4. So if I had taken that out as a GCF, that 1/4, if I multiply that by 0.25, I get that the area under the curve, 1 plus x squared from 0 to 1, is 1.46875. Now, remember, this is just an approximation. And in fact, we know that this is an overestimate because all of our rectangles were above the curve. It's an overestimate. If I do the inscribed rectangles, what we should see is that this will be an underestimate of the area. So the area is going to lie somewhere between RRAM and LRAM. All right, let's see if I can repeat a similar looking picture over here. 1 plus x squared, it's going to look like that. When I exaggerate this a little bit, 1, 2, 3, 4. You just want to try and split that up evenly into those subintervals there. So what would the LRAM look like? Starting from the left side and drawing your rectangles, here's the first height at x equals 0. Second height, third height, fourth height occurs at 3/4, okay? So you'll notice we're still using 1/4 as a height and 1/2 and 3/4, but now the only difference is the last height was, in this case, at x equals 1. Now we're including the height where x equals 0. So if I find all of these and add them up, it's going to be the same thing as these, but instead of f of 1 at the end, it's going to be with f of 0. So it's going to be 1/4 of f of 0 plus f of 1/4 plus f of 1/2 plus f of 3/4. Okay, that's going to be the total area under the curve here using inscribed rectangles, which we determined would be an underestimate of the true area. All right, can I fix this real quick from what I did earlier? What did I have? I had all those same heights there, 1/4, 1/2, 3/4, except I don't want y1 of 1 anymore. I actually want y1 of 0. So if I can just replace that with a 0, boy, that was pretty easy. Don't forget to multiply by 0.25 to get that the area as an underestimate is 1.21875. Okay. So I don't know. I mean, how could I get a better approximation if this is over and this is under? I guess you can average those together. Maybe that would be a decent approximation of the true area under the curve. But what I'll tell you in the next example, as I'm not going to do all these with you, I want you to try LRAM and try RRAM. I'm going to do MRAM with you, though, just to make sure that we understand what MRAM means. We have a left rectangular approximation method. We have a right. And then for M, it's going to be the midpoints. And this should be even a little bit better. You'll see why in a second. Our function's changed. We're looking at 6 minus x squared. We want to find the area from 0 to 2 using 5 rectangles. All right, so let's see if I can draw a good picture of 6 minus x squared. from 0 to 2? Well, I know it's a parabola that got moved up 6 and is upside down. So the curve's going to look something like this. And I know that 2 actually is just before where we hit that root. That root would be at radical 6, which is a little bit bigger than 2. So if I put 2 here and 0 here, I want to make 5 rectangles over this interval. So we need 1, 2, 3, 4, and that would be the 5th rectangle. Okay. Now, what's delta x in this case? Delta x would be 2 minus 0 over, we wanted 5 rectangles. So now my delta x is 2/5, or 0.4. So if each of these locations is 0.4, this would be 0.4, 0.8, 1.2, 1.6, and finally x equals 2. How do we do the midpoints? Well, in between 0 and 0.4, the first height that you're going to draw is the middle of this interval, which is at 0.2. And notice how if this is the height of the rectangle, you're going to get part of the graph that is under, and then part of the rectangle that's over. It's a little tough to tell for that first one maybe. But when I go to the next midpoint, remember this is 0.4 and this is 0.8. So now the height's at 0.6. It's going to start to become a little bit more apparent that if that's the height of my next rectangle, when I draw across through that height, part of it's an under estimate, but then another part of it's the over estimate. The next height here would be at, actually x equals 1 is the next one. We got a little under, but then we got a little over. Sorry, these rectangles are starting to get a little off kilter here, guys. All right, we need 2 more rectangles. We need 1 here and 1 here. So that would be at 1.4 and finally 1.8. So we got one that looks like this, and then one that looks like this. Sorry that those got a little bit off. The most important part of this is that we realize that when we're finding the midpoint, the MRAM, we can see we get a little under and a little over. So those kind of balance each other out pretty nicely here to get one of the better approximations for the true area under this curve. So similar to what I did up here with all my delta x's equaling 2/5, to find MRAM, I'm going to say it's 2/5 of. The first height is f of 0.2. Okay, that's the midpoint of the interval from 0 to, that would be 0.4. So it's going to be f of 0.2 plus f of 0.6 plus f of 1 plus f of 1.4 plus f of 1.8. Okay, so those are all my rectangle heights times the base length of 2/5. So if I change my function in y1 to 6 minus x squared, I think this is probably the easiest way to go about it. Maybe you guys have better ways than I do. All right, 6 minus x squared. So I'm going to do 2/5 times, let's do y1 of 0.2 plus y1 of 0.6. Okay, we need y1 of 1, y1 of 1.4, and finally y1 of 1.8, close parentheses twice there, and the MRAM winds up being 9.36. Okay. So I do want you to try the other two. What I'll tell you is if you think about what RRAM would be, in this case, based on the inflection of the curve, RRAM is going to be the underestimate. You're starting on the right side at x equals 2, and all those rectangles are going to be underneath, whereas RRAM in this one was the overestimate. So just be careful as far as that goes. LRAM, start on the left side. If you start on the left side of the interval, all those are now going to be the circumscribed rectangles for LRAM. So go ahead and try those two, see if you can get the two areas for RM and LRAM and see, double check, see if 9.36 is a good fit for the in-between. Probably one of the better approximations than maybe just having LRAM or RRAM there. Last thing we're going to do really fast in this lesson is talk about how we can use the calculator to do RAM. And one of the programs that I gave you when we transferred some calculator programs over is a program called RAM. So it's pretty awesome. If you come over to the calculator and you hit program and you look at option 3, which is RAM, I actually have to go back and change my function. So we're back to 1 plus x squared here. Okay. So we're going to look at the area for LRAM, RRAM, and actually it gives you MRAM as well for 1 plus x squared from 0 to 1 using 4 rectangles. So let's see, if I go to program, choice 4, or sorry, oops, not slope fields. I got too excited. Program choice 3 for RAM, hit enter. It's going to say what's A. So A is the lower bound of 0. What's B? The upper bound of 1. And finally, how many subintervals do we have? We have 4 subintervals. We have the following. LRAM is 1.219. Maybe I'll go all the way out because these decimals terminate. So 1.21875 for LRAM. MRAM in the middle is 1.328125. And RRAM is 1.46875. Okay, so there we have it. And if we go back a half second here, that was the same example that we did right here. And notice how RRAM was 1.46875. And notice how LRAM was 1.21875. Perfect. We're doing this whole process correctly, which is perfect. All right, I'm going to have you guys try this one. But just for the last one, I want you to just kind of compare what happens at n equals 4, n equals 8, and n equals 16. This happens for these next two examples for the functions that are given. So for go back to y equals, change it to the square root of 4 minus x squared. Okay, so once you have that changed in y equals, go ahead and quit there, go back to programs. We want RAM, hit enter. So what do we've got? We're looking for the area from 0 to 2. So 0 to 2 using, first of all, 4 rectangles. Okay. So we can get those. And what I want you to start thinking about is the more rectangles we have, what should we expect to happen? So left, mid, and right for this one is 3.496. Middle is 3.184. And the right is 2.496. Okay. If I go to n equals 8, run the RAM program again, still from 0 to 2, but now choose 8 rectangles. So I want you, one thing we're going to talk about tomorrow is as we increase the number of rectangles, what's happening here? So we get 3 points now for the left, 3.3, it would round to 40. The middle is 3.157. The right is 2.8, and that would round to 40 as well. Okay, so you guys go ahead and do n equals 16 and try this last one as well. We'll go over the results tomorrow, and we'll talk about what's happening here as we increase the number of rectangles. And it's pretty awesome. We have a program to calculate some of this for us. Okay, that's it for me for today. Have a great rest of your day. We'll see you guys next time.